Imagine while walking a busy city, suddenly the ground beneath you collapsed. And this is what exactly happened on 23rd of August 2024, where a sinkhole suddenly formed and shocked the public at Jalan Masjid India, Kuala Lumpur. Therefore, this case study focusing on sinkhole incident happened at Jalan Masjid India, Kuala Lumpur. Jalan Masjid India is a densely urban populated area where surrounded by shops, roads and daily public activity. Because of its busy environment, any ground failure happens at the area can pose a serious risk to public safety and infrastructure. So, what is exactly happened? In this incident, it involved a sudden ground collapse, or also known as sinkhole or subsidence event. According to the investigation report, the main causes of this incident happened was from the failure of corroded sewer pipe combined with unstable soil conditions and heavy rainfall. Initially, many people thought that the main causes of this incident happens due to limestone, but the study confirmed that limestone located far or much deeper underground and not the direct causes. This case study is important because it highlights how human activity, such as installation of underground facilities and infrastructure, can trigger the ground subsidence in urban area. It also shows the importance of maintenance, monitoring and engineering design in preventing such as a failure or issue happen again in the future. In the next sections, we will further explain and understand what is exactly happened beneath the ground.
To understand the Jalan Masjid India incident, we must look beyond the surface and identify it as a complex engineering problem involving anthropogenic ground subsidence. Number 1. The nature of the problem. Ground subsidence is typically a slow regional process. However, this incident was an infrequently encountered sudden cover collapse. What makes this case particularly unfamiliar to local practice in the geological context. While Kuala Lumpur is known for its limestone or karst topography, the Masjid India area actually sits on the Canny Hill Formation consisting of schist, phyllite and quartzite. Under normal conditions, this is considered stable ground. The problem here was anthropogenic, meaning it was human-induced rather than purely natural. Number 2. Multidimensional reasoning. To critically analyze this issue, we must evaluate it through 3 key contexts as required by the framework. First, the safety and health context. The suddenness of the admitted deep collapse in high-density commercial zone poses an immediate and tragic threat to life. Second, the legal and regulatory context. This incident exposed the complexity of the regulatory compliance. Under the Street Drainage and Building Act 1974, there is a significant legal challenge in defining the maintenance liability between the local authority DBKL and the utility asset owner IWK. Finally, the societal and economic context. The collapse led to loss of public confidence in urban infrastructure safety. Economically, the 400 road closure and subsequent search operation forced local business to halt activities, impacting the livelihoods of the community for months.
As we saw earlier, the sinkhole at Jalan Masjid India was not just a random accident. So, what actually caused the ground to collapse? First, Kuala Lumpur is built on limestone ground. Over time, groundwater slowly dissolves the limestone and creates empty spaces underground. From the surface, the road may look normal, but underneath, there can already be hidden cavities. Second, leaking water or sewer pipe can wash away soil underground. This process weakens the ground support and creates small underground tunnels. When the soil becomes too weak, the surface can suddenly collapse. Third, heavy rainfall also affects the ground condition. When groundwater levels go up and down quickly, the soil becomes less stable, especially in the areas that are already weak. Lastly, the busy urban environments adds more pressure. Heavy traffic, buildings, and constant vibration put stress on the weakened ground and can trigger the collapse. In conclusion, the Masjid India sinkhole happened because of the both natural ground condition and human-related factor.
23 August 2024, a tragic admitted deep sinkhole at Jalan Masjid India become a wake-up call for the urban Malaysia. But the engineering safety is not just about soil, it's about the compliance, stakeholder, and the regulations, and also the stakeholder. To prevent such disaster, we must internalize the regulation and the stakeholder roles that form our safety nets. Our first line of defense is the Street Drainage and Building Act 1974. Section 4 mandates the local authorities to maintain the public street, while the Section 70A governs the earthwork. However, the Section 95 presents the challenge, offering a legal immunity to authorize even during negligence. Upon our case study, advocates to overcome through the stricter international standard. Beyond this, the Local Government Act 1976 established the autonomy and the accountability of our city council. Most importantly, as the August 2004, all the KL construction application must now include a certified geotechnical studies. Effective engineering requires coordinates stakeholder ecosystem, which is DBKL, which is Dewan Bandar Raya Kuala Lumpur, leads the land structure analysis and urban utility mapping. Indah Water Consortium, which is IOWK, is responsible for the integrity of the sewerage system, which is vital, such as the pipe failure. Limestone was identified at the Masjid India course. For the technical expertise, we look the Institution of Engineering Malaysia (IAM) and the Malaysia Geotechnical Society, which is MGS, to provide the expert props and the monitoring. Finally, the Federal Territorialities Ministry provide the policy oversight necessary for the public safety. By integrating of this role and strictly adhere to the SIDB construction industry standard, we move from the reactive repairs to a proactive prevention. Utilizing the ground penetrating radar and regular integrity audits ensure that our site's infrastructure is never out of mind. Through this case study project, we advocate for a culture where regulations are not just rules, but the foundation of public trust.
First, the proposed solution is advanced underground utility mapping. This approach uses technologies such as ground-penetrating radar, sonar waves, geophone mapping, and satellite technology to create accurate 3D maps of underground infrastructure. This is important because many other areas in Kuala Lumpur contain overlapping and unrecorded utility lines. Through accurate mapping, authorities can identify underground voids and aging pipelines before failures occur, helping to prevent sudden sinkholes and road collapses. The solution supports SDG 9 and SDG 11 by improving infrastructure monitoring and promoting safer, sustainable urban development. The second solution is mandatory geotechnical audits and ground scanning before approving any development project. This involves soil investigations, borehole sampling, and geophysical scanning, with all results analyzed by accredited geotechnical engineers. Kuala Lumpur's limestone soil structure makes the ground vulnerable to instability and underground caverns. By identifying these weak zones early, engineers can design suitable foundations that avoid unstable areas and improve structural safety. This solution mainly supports SDG 11 by reducing risks from structural disasters and ensuring safer urban development. The third solution is proactive infrastructure maintenance and upgrades. Instead of waiting for failures to happen, authorities should implement planned preventive maintenance by replacing aging water pipes and sewerage systems before they become damaged. This is important because leaking underground pipes can wash away soil and create hidden voids beneath roads and buildings, eventually leading to sinkholes. By reducing leaks and maintaining secure pipelines, the solution helps strengthen infrastructure resilience, supports SDG 6 through better water management, and SDG 9 through sustainable infrastructure development. The fourth solution is periodic lifecycle inspections and continuous monitoring. This involves regular inspections of roads, footpaths, retaining walls, and drainage systems, including compliance with the mandatory 10-year inspection under the Street Drainage and Building Act 1974. Although buildings may have strong foundations, surrounding infrastructure still depends on soil stability and is vulnerable to erosion and settlement. Continuous monitoring allows engineers to detect early warning signs, such as uneven ground settlement or water bonding, before serious failures occur. This solution supports SDG 11 by ensuring safer and more accessible.
Now it's my turn. Okay, my name is Amir. Okay, as civil engineers, we have a professional responsibility to prioritize public safety and long-term resilience over temporary fixes. I will now critically evaluate the societal and environmental implications of the proposed solutions for the Masjid India sinkhole. Okay. The analysis is grounded in engineering judgment and technical literature, focusing on how this intervention reflects a real-world professional practice in karstic terrain. From a societal context, a sinkhole is a local collapse that can destroy roads and utilities, posing an immediate threat to life in high-density urban areas. Our advanced underground utility mapping and mandatory geotechnical audits directly mitigate this by identifying hidden voids before they lead to sudden surface failure. Beyond immediate public health and safety, these solutions restore public confidence and prevent socio-economic disruptions, such as business interruptions and loss of property values in major commercial hubs like Kuala Lumpur. By mapping the depth of limestone caverns, we ensure the structural integrity of the surrounding community. Moving to environmental impacts, our focus is protecting urban infrastructure from the risk of limestone dissolution. Our proactive infrastructure maintenance replaces aging, leaking pipes that are the primary human-induced catalyst for soil erosion. Okay. This aligns with the Sustainable Development Goal number 12, responsible consumption and production, as we prioritize resource efficiency and lifestyles in harmony with nature. Furthermore, our approach supports Sustainable Development Goal SDG number 11, sustainable cities, by ensuring water management system and soil porosity are not permanently damaged by subsurface ruptures, thereby preventing environment contamination. Finally, we address regulatory compliance through periodic life cycle inspections and strict adherence to Section 85A of the Street Drainage and Building Act 1974. While these proactive measures involve higher initial costs and complex interagency coordinations compared to a fixed when broken model, the long-term impact is a significant reduction in structural disasters. Our engineering judgment concludes that the trade-off of higher investment is necessary for the resilience of Kuala Lumpur's infrastructure. That's all from me. Let's go to the next part.
The mitigation of sinkhole risk in Kuala Lumpur cannot rely on any single intervention. It demands a cohesive synergy between advanced technological mapping, rigorous geological science, diligent infrastructure upkeep, and strict regulatory enforcement. In conclusion, the 2024 sinkhole incident serves as a critical wake-up call for urban management in Kuala Lumpur. The sources indicate that the city's safety depends on moving beyond crisis response toward a systematic integration of technology, mandatory soil analysis, and proactive infrastructure maintenance. By addressing the intersection of natural limestone geology and aging man-made utilities, the government can better protect the community and ensure long-term urban resilience.